everyone. Welcome to JG Chemistry. Guys, in this video we are going to discuss the symmetry operations in group theory. It is the topic on demand and very important for CSIR-NET and GATE students and those who are appearing for any competitive exams for M.Sc chemistry students. And in this video we will learn about the symmetry elements, the symmetry operations and its application. So basically the symmetry and the group theory, it has very important application in molecular spectroscopy, in quantum mechanics to find out the structure and geometry of the molecule. So let's begin. So for that we will see what is group theory. So basically it is the systematic discussion of symmetry which is called group theory. Here we will categorize the molecules based on the symmetry and put it into the respective groups. So here how we do that and what is the application of group theory to find out the geometry and the electronic structure of the molecule. And since we say that the group theory is basically the discussion of symmetry, so we will see what is symmetry. Basically a certain portion of the object, if it looks like exactly the similar to the other half, then we say it is the symmetrical object or it is a symmetrical molecule. And where it has application, it has application in molecular spectroscopy. So if you have studied molecular spectroscopy like vibrational spectroscopy, ultraviolet spectroscopy, then you might be familiar that certain molecules are active to that radiation and certain are inactive. So based on the symmetry, one can decide whether the following molecule will be active or inactive or whether it is going to absorb the radiation. So symmetry has importance in molecular spectroscopy, in quantum mechanics, and to find out the structure of the molecule and find out the stereochemistry, whether it is D isomer, L isomer or it is meso. So based on the stereochemistry symmetry, you can decide the stereochemistry of the molecule. And to understand this, we should know the basic knowledge of the geometry of the molecules based on the Vesper theory to find out the and to have an understanding the knowledge of symmetry elements. What is symmetry elements then? Symmetry elements are the geometrical elements like line or plane with respect to which we will perform the operation. It is completely imaginary and we will see how we will do that. So there are total 5 symmetry operations. We will discuss first, which is rotational axis of symmetry represented by Cn, axis of symmetry. So you can say what is rotational symmetry or axis of symmetry, that an imaginary axis around which the molecule is rotated, and when it represent indistinguishable configuration, then we say the molecule is having the rotational axis of symmetry. So to understand this, we will take one example, very basic example, water molecule. So it has the band structure. We know the shape of the water molecule is band, and if you see it has 2 hydrogen, let's represent it by 1 or 2. So after 2 times of rotation, it will represent the indistinguishable molecule. Okay, so that we will see indistinguishable configuration. Since n is 2 here, we can represent here in 360 by n, that is 2, 180 degree rotation. So if you rotate this H2O molecule by 180 degree 2 times, then it will show you the same indistinguishable configuration, and so we represent the Cn is 2 here, so C2 axis of rotation. How? So this is the shape of the molecule water, and we can consider to distinguish the 2 hydrogen, let's say 1 and 2. So if you perform 180 degree rotation, that is C2 operation, this is the axis of rotation which is imaginary. 180 degree if you rotate, then you can see the H2 will come in place of H1 and H1 will in the place of H2. So now this is not the indistinguishable with respect to the first molecule. So first configuration, so we will rotate it again by 180 degree, and you can notice that after doing this again we get the molecular configuration which is indistinguishable with respect to the first one. So both are same. Now 2 times we have rotated it, so we can say here you have C2 axis of rotation. So C2 and axis of rotation, so C2 one time, and we also represent it C2 2 because ultimately 2 times you have rotated it. C2 2 is nothing but it is equivalent to the E, which is called identity element. We will learn about it later in this video. So two operations are present in this molecule, E and C2. There are other operations also, we will see later on in this other operations, symmetry operations. So since we are focusing only on rotational axis of symmetry, we will talk about only the rotational axis here, or axis of symmetry. We have other elements and symmetry also present, we will discuss it later. So ammonia is the next example, and we know there are 3 hydrogen, so it has to rotate 3 times to get the indistinguishable, and should be 3. We say C3 axis. So how many degree rotation you have to do? 360 divided by 3, that is 120 degree rotation. And we know the shape of the ammonia molecule based on the Vespa theory, it is pyramidal. So we can distinguish again by 1, 2, 3, and if you consider this axis of rotation which is passing through nitrogen, it is now rotating by 120 degree, and if you do it once, you can notice that H3 will come in place of H1, and then H1 will go in place of H2, and H2 will come in place of H3. 120 degree rotation, so but it is not indistinguishable to the first, we will rotate it again by C3. Same procedure will be there, 120 degree rotation. Now you can notice that after performing the third C3 operation, you will get exactly the indistinguishable configuration, that is H1 will come into H2 place, H2 will go to H3 place, and H3 will come into H1 place. So that is the first structure itself, the first configuration. So total we have to perform 3 times C3 operation. Therefore we can say C31, C32 and C33, which is 3 is cancelling each other, it is equivalent to identity. So C3 axis of rotation is present in ammonia. BF3, we know the shape that it is planar. So BF3 you can write planar, and the axis of rotation is passing through the boron perpendicularly, you can notice here. And if you rotate again by same C3 axis 120 degree, imagine it has to rotate by 3 times. But here, since it is planar molecule, and it can possess the C2 axis of rotation also. How here the C2 axis is passing through boron and one of the fluorine. So the atom which are on the axis of rotation, C2 axis of rotation, are constant, and then you can imagine the 2 fluorine is behaving the same like water molecule. So it has 3 C2 axes respectively, because we have 3 C2 axes. As you can notice this green line, we have 3 C2 axes here, and this blue line represent the molecular plane. So the molecule, since it is planar molecule, it is having the molecular plane. So your axis of rotation and C2 axis is perpendicular to each other. So basically we have one C3 axis and 3 C2 axis of rotation here. If you go for XeF4 or PTCl4 2-, which is having the square planar shape, again planar molecule. So all planar molecule possesses a C2 axis and it has the molecular plane. Square planar, if you arrange the fluorine 4 in the same arrangement, so you can have here one C4 axis, that is after 4 time rotation you will get the indistinguishable configuration. So it has C4 axis of rotation, that is the principal axis of rotation, and then with respect to, you can notice here 2 fluorine and xenon, one axis is passing, that is C2, and other fluorine you can imagine just like the linear molecule. So it will 2 times rotation, it will give you the indistinguishable. Similarly you have here vertical line, one C2 axis, and 2 more C2 axes are present which is passing through xenon, and between the two the dihedral angle between the 2 fluorine atom respectively. So total here 4 C2 axes are present, represented by green line, and the principal axis of rotation is represented by red line. So we have one C4 axis and 4 C2 axes are present here. So we can make a note out of this that C3 and C4 axes are the imaginary line which is passing through xenon or platinum, which is perpendicular to the molecular plane. So you can see here the molecular plane, and which is perpendicular, the axis of rotation is perpendicular to it. And any CN axis is associated with n number of symmetry operation that we have seen. If you are having C3 here, so we represent C31, C32 till you achieve C33, right? So it depends, the Cn will go till CNN operation. And finally you have Cn plus nC2. If you notice here, we have C3 axis, then we will be having 3C2. We have C4 axis, then 4C2 will be there. So you make a note, and this will be a trick also to find out how many C2 will be there. So you can make a note also that all the planar molecule possesses the nC2 axis of rotation with Cn axis of rotation. Now we consider the next example, C5H5, that is cyclopentadienyl anion minus, you can make it here, and the structure of cyclopentadienyl anion is, you can see C5 is the principal axis. 5 times if you rotate it, you will get the indistinguishable, and it has again 5 C2 axis of rotation. As we know, it is again planar molecule, and you can notice it with green line. So you will be having 1 C5 and 5 C2. Similarly for benzene, it is being planar. You have 1 C6 axis and 6 C2 axis of rotation. So you can notice Cn plus nC2 axis of rotations are there in all planar molecule. And since we have written that Cn axis is followed by CNN operation, so you can see that we have written here C61, C62, which we can represent 2 by 6 like 3. If you count this table, C3 which is equivalent to C3, then C63, so we can represent it C2, then C64 which is we can represent C23, and then C65, C66 is cancelling each other, so it is equivalent to identity. So these all operations will be there in benzene molecule. Now we'll come to the next symmetry operation, which is called plane of symmetry, represented by sigma, which is also called reflection symmetry. So what is that? When any imaginary plane you are having which represent the other half of the molecule as indistinguishable configuration, then that plane is considered as the molecule is considered as having the plane of symmetry. So again we'll take the same example to have a look on plane of symmetry, water. So there are actually 3 kind of plane of symmetry. One is called the horizontal plane of symmetry, or we also call molecular plane of symmetry, and there is sigma v, vertical plane of symmetry, and sigma d, dihedral plane of symmetry. So in this we have the green plane representing the sigma v, vertical plane of symmetry. So if you have any imaginary plane here, you can consider it like a mirror. So you can notice, if you have a mirror with respect to the oxygen, it is representing the indistinguishable configuration. So it is having one vertical plane which consists of the principal axis. So vertical plane always consists of the principal axis. We have the C2 axis in this plane only. And then it has the horizontal plane also. So if you imagine a plane putting just below this water molecule, then you can see exactly this water molecule shape on the other side of the plane. So it has the horizontal plane of symmetry as well. So sigma h is also there. So you have planes that are perpendicular to the CN axis, that is called sigma h. Sigma v, plane containing the principal axis. So we have seen this sigma v also. Now you can notice ammonia. Okay, so here in water molecule, if you see, this is a bent molecule. Okay, so you just make a note whether you are able to see this sigma h there or not. Okay, so you have to find out For sigma h or molecular planes are normally for the molecule which are having the plane of symmetry. So you won't be having the plane of symmetry for the water molecule. This I have just shown you what do you mean by molecular plane, but it doesn't have in this molecule. Water molecule having only the vertical plane of symmetry. So here in ammonia also you have 3 vertical plane of symmetry, so which is consisting of your axis of symmetry here. Now you have on this vertical plane one nitrogen and hydrogen, so this is constant, and other you can see if you have a mirror on this, the two are indistinguishable. Similarly, if you rotate, the H2 will go on S3 place or H1 may come on S3 place. So like that you have 3 sigma V planes for this molecule. So basically it has 3 sigma V vertical plane which consist of the principal axis. Now we have another example, BF3, which is planar molecule. Now as I told you, all planar molecules will have the horizontal plane or molecular plane, so you have that. Along with that you have 3 sigma V, each is passing with 1 boron and 1 fluorine, so other is looking like a mirror image. So you have 1 horizontal plane and 3 sigma V for BF3. Since we have already covered the rotational axis, so C3 axis of rotation, which is followed by NC2 axis, sigma H is there and 3 sigma V are there. So far we have covered rotation and reflection axis of symmetry. So basically all planar molecules have molecular plane as one of the plane of symmetry, that you can make a note. XCF4 square planar, this should have again horizontal plane. Along with that you have here 2 sigma V, and you can notice here we have 2 sigma D, dihedral plane of symmetry. So all 3 are there. Now how to distinguish between sigma V and sigma D, I'll tell you a trick, that you can notice here that you have a plane which is passing with 1 xenon and 2 fluorine. So maximum number of atoms are there, 3 atoms. So this is, and it consists of the C2 axis of rotation also. So this is represented by sigma V. Similarly, other side also you have, so 2 sigma V are there. Now if you notice the sigma D, which is passing only through the xenon atom, so you can see the plane which is passing with the minimum number of atoms, and which is also bisecting the angle, the dihedral angle between the 2 fluorine atoms. So you can see this is the dihedral angle, represented by blue. The plane which is bisecting the dihedral angle with minimum number of atom is represented by sigma D. So basically this again having the C2 axis of rotation, the axis of rotation is there. So there is a very thin line to differentiate between sigma V and sigma D, which is based on the number of atoms you can make a note. So it has 1 sigma H because it's a planar molecule, 2 sigma V and 2 sigma D. Followed by, you have done already rotation, C4 axis of rotation, NC2, that is 4C2 operations. With the same definition and trick is mentioned here. For benzene also you can see here same, the maximum number is passing with the plane passing through the maximum number of atoms is sigma V. The minimum number of atom is sigma D. So basically you have 1 horizontal plane, 3 sigma V and 3 sigma D are there, followed by the rotation axis. So we will make a note that the same which I have already told you about the dihedral angle, and in general you can see that all the regular polygonal structures are having n by 2 sigma V and n by 2 sigma D planes, where n is the even number of equal sides in polygon. So in benzene you have n6, 6 by 2 is 3 sigma V and 3 sigma D planes. So when your n is even, like in XCF4 it is 4, which is even, so you have 2 sigma V and 2 sigma D there. But when you have n is odd, then the dihedral angle will not exist. So the example is cyclopentadiene C5H5, which is having the odd number n is equal to 5. So here you will have 5 sigma V. So you have C5 NC2, that is 5C2, sigma H is there because it is a planar molecule, but being odd number it has only 5 sigma V. It's not, you have sigma, you don't have sigma D here. Next symmetry operation is center of symmetry represented by I. How to find out the following molecule is having center of symmetry? The definition is, if you have draw imaginary line from the center of the molecule and extend it to the other side with the same distance, and if it meets a similar atom, then we say the following molecule possesses a center of symmetry. Now how to understand it, we'll take one example. So this is the molecule HCF2. Now whether it has a center of symmetry, so we have seen that an imaginary line, so from the center of the molecule, center is seen on here. So if you draw imaginary line on the left hand side, it meets fluorine. And if you imagine imaginary line, draw imaginary line on the right hand side with the similar distance, and if it meets a similar atom, left side is boron, right is also left is fluorine, right is also fluorine, it meets similar atom, then we say the following molecule possesses the center of symmetry I. Similarly for carbon dioxide, it meets oxygen on one side, also other side oxygen, so it has center of symmetry. So if you say trans dichloroethylene, you can see the center of the molecule is between the C double bond C, and if you draw an imaginary line, it meets chlorine. On the other side, similar distance, it meets chlorine. And similarly for hydrogen, so it possesses the center of symmetry. So inversion, also it is called inversion, so therefore it is represented by I. Inversion through a center of symmetry is basically, you can frequently see in benzene and HCF4, which is highly symmetrical order. So if you want to see I, you can find in highly symmetrical molecules like benzene, HCF4, CO2, center of symmetry is present. The fourth symmetry operation is called improper axis of symmetry, also called rotation reflection symmetry, represented by Sn. So basically two operations are involved here. Rotation is followed by reflection. Therefore, we call it rotation reflection symmetry. So what is that? If you rotate a molecule by 360 by n degree about an axis, followed by the reflection perpendicular to that axis, then if you get the indistinguishable configuration, the molecule possesses the improper symmetry. So it is represented Sn is equal to Cn plus sigma H. We'll take the same example, trans 1,2-dichloroethylene, and since we have here the C2 axis of rotation horizontally, this C2 twice, if you rotate 180 degree, then you will get indistinguishable image. So first is we have to perform Cn operation, which is C2 here. So C2 axis along this C double bond C, so you will get the position inverse. Okay, chlorine will come in place of hydrogen, hydrogen will come in place of chlorine. Now since we know we have to perform now sigma H operation, sigma H horizontal plane, which is perpendicular of the principal axis. Okay, so we know that always sigma H is perpendicular. So since your C2 axis is horizontal, then your sigma H will be vertical here, perpendicular to the principal axis. And now since your mirror is here, then reflection will come on the other side. So you will see chlorine in place of hydrogen, and you will see hydrogen in place of chlorine. And you can notice this structure is indistinguishable to the first configuration, and so the molecule 1,2 trans dichloroethylene possesses the S2 axis of rotation, that is improper axis of rotation. So basically all planar molecule has improper axis of symmetry. We have seen that all planar molecules have in sigma H, and also you have, if n is even number, you will have sigma D also, and also it has the improper axis of symmetry. And finally you have the most simplest identity symmetry, which is the last symmetry operation represented by E. Basically it is doing nothing to the molecule, and all the molecule exhibits E. The least symmetrical molecule, even it possesses the E element. You can see here carbon is tetravalent, having the 4 different group or ligand, that is there is no symmetry at all. So if you rotate this by either 0 degree or 360 degree, that is C1, you will get the same configuration. That means you have done nothing to the molecule. So basically all molecule possesses the see one axis of symmetry or identity operation. So in that way we have learned about all 5 symmetry operations, which are very important. By seeing the very easy examples, hopefully this particular session will be very important for you, and you might have understood how to perform the symmetry operations. And in the next video we will learn about the point groups. Happy learning.